figure out how to experimentally determine what this rate law should look like, and specifically how we can get numbers for k, x, and y, where k is my rate constant and x and y are the orders of the reaction with respect to A and B. It's very important that we keep in mind that this cannot be determined by looking at a balanced chemical equation. This can only be determined experimentally. And one of the most common methods is what's called the method of initial rates. Basic idea is you run the same reaction over and over again, but you change the initial concentrations of your reactants, and then you measure the rate of that reaction. After that, you can see how the rate changes when you change those concentrations, and through doing some careful analysis, we're going to be able to figure out the order of the reaction and that rate constant. So we'll be able to fill in our rate law here. It's important to keep in mind that the rate constant does have units, but those units change. So we have to be very, very careful to make sure we put the correct units on our rate constant at the very end. So all of these problems look pretty much identical. It tells you that the rate, some reaction was measured with several different initial concentrations, and it always gives you this table. And this table has the concentration of your reactants in a couple columns, and then it measures the rate. So when you see this, this should be your clue, initial rate. This is going to be an initial rate problem, and that's what I'm going to do this procedure. And it always wants us to determine the rate law, including K with units. So these problems aren't that hard, but they are a little lengthy, so let's walk through it step by step. The very first thing I like to do is write my general rate law. So that's my rate equals, and it's always K, and then A raised to the X, and B raised to the Y. Of course, if you have different molecules here, you'll just fill those in, but other than that, it'll pretty much always look the same. So we're trying to solve for three pieces here, K, X, and Y. K we have to save till the very end. We cannot solve for K yet, so we need to start with either X or Y. It doesn't really matter which one you start with. I solve for X just because I like to go in order, but you could solve for Y first. But let's start with X. Since X is the exponent on A, what we need to do are pick two rows where A changes, but B stays the same. So in this case, I'm going to pick rows 1 and 2. And what I'm going to do for those two rows is fill in this rate equation, general rate law up top, with the information from my table. I'm going to do it twice, once for the first row, once for the second row. I always like to look at my rates, and you'll see why this makes life easy, and I pick the bigger number. In this case, that's for row 2, and I'm going to start with that one. See, my rate is bigger in row 2 compared to row 1. So I'm just going to plug that information into my rate law. So the rate here is 0.302 molar per second. That's equal to K. My A here is 0.20 molar. Ooh, that's an M there. Molar. Raised to the X. And my Y is 0.10 molar raised to the Y. So all I've done is plug in this second row to my rate equation. And now I'm going to do the same thing. I'm going to do it with the row 1. So my rate there is 0.150 molar per second is equal to K. Here A is 0.10 molar raised to the X. And B is also 0.10 molar raised to the Y. Now what I'm going to do, that I've written this twice, is I'm just going to make it into a big fraction. So I'm going to divide the left sides and divide the right sides and set the whole thing equal to each other. And I'm allowed to do that because since the bottom part is equal on both sides, it's like dividing both sides of the top by the same number. So mathematically, it works out. When I do this, I see a lot of stuff cancels. My K's cancel out. And then this is why we picked B to not change. Since B didn't change, it also cancels out on the top and bottom, that 0.1 molar. All of my units cancel out as well. So now all I need to do is do a little bit of math. I'm going to do that right here. 0.302 divided by 0.150 gives me 2.01. On the right side, I have this part left. That's the only thing that doesn't cancel, other than the units in there did cancel. 0.2 divided by 0.1. Now notice they are both raised to an exponent, x. But since they're raised to the same exponent, I can do the division inside and then just raise that answer to the x. So 0.2 divided by 0.1 gives me 2. And that whole thing is raised to the power of x. So now I'm going to look at this. So 2.01, that's pretty much 2, right? Within rounding, there's always a little experimental error. So I have to think about 2 raised to what exponent is going to give me 2? Well, pretty easy. In this case, that must be 1. Therefore, x must be equal to 1. We've solved for one of the 3 pieces. So, not too hard, but it is a little long because that's only for the first one, so now we got to move on. So now we're going to solve for y. So we see here I've filled in my rate law with the information I had for x. Now I've set that equal to 1. Now I want to solve for y. I'm again going to compare 2 rows. This time, since I want y, I want b to change and a to stay the same. So I'm going to pick rows 2 and 3 because we can see that b changes whereas a does not. I'm going to do the same thing. The third row has the bigger number, so I'm going to put him on top. So I'm going to do 0.427. And since I know my units cancel, I don't really need to put those. And I have k. X is equal, I'm sorry, a is equal to 0.20 raised to the x. And b is equal to 0.20 raised to the y. Now I'll do the same thing for row 2. My rate is 0.302. I have k, a is 0.20 raised to the x, and b is 0.10 raised to the y. Now we again turn it into a big fraction. We can see that my k's cancel. Since I picked 2 rows where a didn't change, that also cancels. So now I need to just do a little math. So on this side I divide and I get 1.414. And on this side I divide and I get 2, but keep in mind I have that exponent, so 2 raised to the y. Now this one's not as obvious as what we had last time. It's not really, just doesn't come to mind, 2 raised to what power gives me 1.414. So if you're ever not sure, if you can't just look at it and tell, what we're going to use are logarithms. We're going to take the log of both sides. So the log of 1.414, 414 is equal to the log of 2 raised to the power of y. And the reason we use logarithms is because logarithms have this property that if you have something you're taking the log of and it has an exponent, you can move that exponent and put it right out in front. So what we, ignore that. So what we really have is log of 1.414 is equal to 2 times the log, y, go back in time. Don't know what I'm doing here. So we move that y, so we have y times the log of 2, right? Because we got to move that exponent out in front. Well, now it's really easy to solve, right? We can just divide both sides by the log of 2 so that this side cancels out. So y is equal to the log of 1.414 divided by the log of 2. And when we do the math, we just divide those in our calculator, we get 0.5 or 1/2. So half orders are allowed. They're not that common, but they do happen. So we say, all right, fine. That's why we got this weird thing here, because we're not really used to looking at orders of 1/2, but now it all makes sense. So if it's not obvious, you just use logarithms. All right, so now we've got x and we've got y. So last thing is we've got to get k. So now I've just plugged in my x and y to my rate equation. To solve for k, we just pick any row of data and plug in our numbers. I usually pick the first row, no special reason, just do. And I'm just going to do what I did before. So my rate is equal to 0.150 molar per second. Now I have k. A is 0.10 molar, and now I know it's raised to the 1. And b is also 0.10 molar, and now I know it's raised to the 1/2. So what I'm going to do on this side is I'm just going to plug the numbers into my calculator, and in that case I will get, I still got my k out front, and then 4.74. That's 0.1 times, getting ahead of myself. So if I do 0.1 times 0.1 raised to the power of 1/2, what I get is 0.0316. And now I need to pay attention to my units. I've got m raised to the first power, m raised to the 1/2 power, so I'm going to add the exponents, and I get m raised to the power of 1 1/2, or I'm going to turn it into a decimal, m to the 1.5, and that's still equal to 0.150 molar per second. So now I'm trying to isolate K, so I'm going to divide both sides by this number, 0.0316 m to the 1.5. So math-wise, that's really easy. Just plug it in, and I get 4.74. Just trying to pull that out too early. And I have to pay attention to my units. So up here I have m per second, and since it's just an m, I know that really means m to the 1. And I'm dividing by m to the 1.5. So when we divide things, same base number, and we have to deal with their exponents. When we divide, we subtract their exponents. So 1 minus 1.5 is going to give me m to the negative 0.5, right? 1 minus 1.5 is negative 0.5. And then I still have this per second, which we can write as s to the negative 1. So after I do my division, I find my k. And now I can just rewrite my final rate law with everything plugged in. My rate is equal to k, which I know is 4.74, m to the negative 0.5, s to the negative 1, a to the power of 1, b to the power of 1/2. And now I have my final rate law.